Hi, Chris Good here, and here's a lecture on one-way analysis of variance. There's another uh, video like this floating around the YouTube channel, but I thought I'd update it for spring semester of 2019. The example that we use in one-way ANOVA is from a paper on something that ended up being called the Mozart effect. And the idea here is that if you listen to Mozart, you'll get smarter. At least that's what people think of when they think of the Mozart effect. And there's been any number of popular culture, books, CDs, DVDs, etc., arising from this idea that if you listen to Mozart's music, you get smarter. All of this stuff is based on a number of different papers. The first one of note came out in 1993 in Letters to Nature, and is from a group from UC Irvine where they're measuring spatial reasoning in college students after they listen to either music or relaxation or silence. Spatial reasoning is hard to test, but there's a number of different tests that attempt to quantify how well people manipulate things with their mind in space. It could be two-dimensional, three-dimensional, but it has to do with sort of imagining things in different spatial orientations, positions, or otherwise spatial situations. Here's an example. This is called the Raven matrices test. You're supposed to see that there's a blank missing piece here, and you're supposed to fill in the matching piece from the things below. I like the one in the top row of these choices, which is the second from the left, the 3 vertical dots, because it matches the pattern. Matches it both ways. 1 dot, 1 dot, 1 dot, 2, 2, 2, 3, 3. 3 in the vertical orientation and not horizontal, so that top row, second from the left, is the best answer, if indeed that's what the question is. So it's an abstract sort of thing. These are a lot harder. I'm only going to talk about this first one. We talk about the other 3 in class. But number 1, you're supposed to pick of A, B, C, or D, these 4 yellow and green squares, which one best fits into that blank. I really like B, because if you look at how the pattern is changing, the second yellow and green square box there is what the first one would look like if you rotated it 90 degrees clockwise. Similarly, the third one looks like what the second one would look like if you rotated that thing 90 degrees clockwise. So if you did that to the third one, I think it would actually, it would look like C then. So I like C as the answer to this one. It looks like it's you can't pick this thing up. It's on the screen. You have to mentally imagine what these things would look like as you turn them in different orientations. That's from part of an IQ test called the Stanford-Binet, and it measures spatial reasoning. The authors of this paper, Rauscher, Shaw, and Kai, figured that since we think about music and in terms of spatial in spatial terms, that maybe it has something to do with these type of tasks. For example, on musical instruments, you can make notes by pressing keys or fretting strings, or manipulating other things, where the notes that come out are similar in pitch on keys that are close together in space, right? We talk about music in abstract terms using spatial words like low notes and high notes, and there's a C above middle C or below middle C, etc. So we're already thinking about music in a directional sort of way. Maybe something that's super complex with notes with lots of complex mathematical relationships actually might sort of prime one to be thinking in complex abstract spatial terms, and so you might expect your performance on these type of tests to be better if you're primed with some complex musical stimulus. And the piece they selected, this Mozart piece, and we'll listen to it in class, is kind of complicated. So maybe it's not surprising that they found that people on average, after they listened to Mozart's music, scored higher than after they listen to relaxation tape, which is like nature sounds, babbling brooks, ocean sounds, white noise, or listening to nothing at all, silence. The problem with this is you want to know whether the differences here are significant. Now, you could do 3 different t-tests. You could do one t-test comparing music and relaxation, another comparing music and silence, and another comparing relaxation and silence. But every time you do that, it comes with an elevated risk of type 1 error. You have a certain level of risk of making a type 1 error when you do one t-test. If you do another t-test on similar data, right, you're including the same group, that's a multiple comparison that, for reasons that we described in class, is going to artificially, well, not artificially, it actually, for real, increases your risk of making at least one type 1 error somewhere among those 3 t-tests. The compound probability of making a type 1 error is not additive, so it's not simply that, oh, you have a 5% for one and a 5% for the next one, so it must be 10%. It doesn't work exactly that way. We talked about how to compute that in class, but it does increase the risk of type 1 error. So instead of using a t-test or 3 t-tests, we use something called the analysis of variance. It's a really cool statistic. You can use it with any number of conditions. You can use it with just 2 conditions. But when you have more than 2 conditions, you have to use ANOVA. You can't do multiple comparisons without some other correction to the type 1 error rate. ANOVA is one of those ways of correcting that. So why do we not do 3 t-tests comparing 3 means? Because it would increase the risk of type 1 error too much. So consider these scores. These are 15 different scores from 15 different individuals under 3 different conditions: 5 under Mozart, 5 under relaxation, and 5 under silence. The scores are not the same as each other. They're different. There's variability. We could measure that variability by looking at how far apart these scores are from the mean. You know that we would do that by getting deviations of each score from the mean, squaring those deviations, and then we could look at one number. The sum of all those squared deviations is an indicator of how different these numbers are from each other. Here are 3 other numbers. These are the means for each group. The mean, and I know these don't match the graph I showed you. I've made up these data. They're not from this. They're not from the Rosh Hashanah Kai paper. But you might have seen means like this if you did the study on an 8-point IQ scale. So the mean for Mozart is higher than relaxation, and that's higher itself than silence. These means have variability too. We could measure this variability by essentially looking at sum of squares of these 3 numbers several times over, one for each set of scores technically. But let's instead think about why the numbers are different from each other. Well, obviously there might be a treatment effect. What you listen to might determine your IQ. So that's one thing, a possible treatment effect. But this is an independent groups design the way we're looking at it now. So it could be that they're just different people, and we just randomly got people who have a better IQ in one condition than another. So the effect of individual differences, that might be a reason why these numbers have variability. And the third reason is that other aspects of chance besides there being different people may bear on the variability of these 3 means. So the person who scored 1 in the silence group might have scored better if they hadn't stayed up all night the night before, but that was just a chance thing because their pet was sick or something like that. The person who got a 7 in the Mozart condition might not have improved their spatial reasoning by listening to Mozart, but might have been inspired by something else. Maybe they had been reading a book before about spatial reasoning and had practiced by accident on the way to the study. So there's 3 reasons why there is variability among these 3 group means. Maybe a treatment effect, individual differences, and other aspects of chance. Let's look within a condition. Within the relaxation condition, there's variability too. Not everybody had the same IQ score. Why? Well, it can't be a treatment effect because we treated all the people in the relaxation condition the same. We tested them under controlled conditions, and so there's no difference in the way they were treated, so no treatment effect. But they are 5 different people, so individual differences play a role, and that same old chance that we talked about before, where one of these people might have been distracted during the test, or not tried hard because they were tired, or tried extra hard because they were inspired. chance in people are different are the reasons why variability within each treatment condition exists. We can measure this as well. So let's talk about how to measure variability between these conditions as well as within the conditions. But we're going to start with measuring the total variability. All 15 scores are, some of them are different from some other scores. We can measure that difference by looking at the sum of the squared deviation from the average score, which we're going to start calling the grand mean. The grand mean is just the sum of all the scores divided by the number of all the scores. And we can get deviations of every score regardless of what group they were in from that grand mean. We'll square those deviations, sum them up, and that's our total sums of squares, and represents the total variability of our entire data set. Analysis of variance is literally that. The word analysis means to split something into its component parts. And we're going to use ANOVA to split the total sums of squares into sum of squares between treatments, how different are the means from each other, and sum of squares within treatments. Within a condition, how different are the scores from each other. There's a couple of new equations here, and they require a couple of new statistics that we haven't described previously, and they include these. G is very important. G is the sum of all the scores, and we're also going to look at big N, which is not pictured here except in the equation. Big N, the uppercase N represents the number of all the scores, regardless of treatment condition. Lowercase n now refers to the number of scores in a particular condition. So you have a little n for the Mozart group, a little n for relaxation, and a little n for silence. And in this case, they're all the same, n equals 5 for each one. But they might not be the same. So you may be able to do an ANOVA where you have 5 scores in one, 7 in another, and 10 in another. Some other restrictions apply, but we're not going to get into them here. The other new statistic is called T. We do a T for each condition. That's why I put the subscript K there, just to remind you that you have more than one T. And you have as many T's as you have conditions. And conditions is K. K is the number of conditions you have. So for each condition, there's a T that is simply the sum of the scores for that condition. So we have a T for Mozart, 5 plus 7 plus 4 plus 4 plus 4, that's 24. For relaxation, there's a T of 18, that's 4 plus 6 and 3 and 2 and 3. And for silence, the T is 13, 2 plus 5 plus 3 plus 1 plus 2 is 13. We do T because we follow this computational formula for sum of scores between treatment, in which we take those T's and we square each one and divide by the number of scores that contributed to that total. And then we add those all up for all 3 groups. So to compute sum of T squared over n, we would take 24, that's the T for Mozart, square it, divided by 5, which is the number of scores in the Mozart condition. And we'd add that to 18 squared over 5. And 13 squared over 5. So you add all those quantities up, and then from that you subtract the sum of all scores squared. So you square G, you add up all 15 scores and then square them, and you divide by 15, which is n, the big number of scores. So one more time, sum of scores between treatments. This is the sum of T squared over little n, where T is the total within a group, and n is the number of scores within a group. You do that for all of your groups. Add all of them up. And from that quantity, sum of T squared over n, you subtract the quantity G squared over big N. That's sum of squares between treatments. And if you know sum of squares total, you can then get within treatments sum of squares by subtraction, because between plus within equals total for sum of squares. And we've got between. There's also a formula for calculating sum of squares within treatments. And it's simply the sum of squared deviations of all the scores from their mean. So for the Mozart group, you'd subtract 4.8 from each one of your scores. That's the deviation for each one of the Mozart scores. Square those and add them all up. For the relaxation, it's 4 minus 3.6 squared, 6 minus 3.6 squared, etc., right? You subtract the mean from the group from all the scores within that group and get sum of squares. Then you add up all 3 of those sums of squares for each condition to get the sum of squares within all 3 of your treatments. And that quantity within treatment sum of squares plus between treatment sum of squares will be equal to the total sum of squares. You can always check your math by doing all three and make sure everything adds up. But I thought it was called analysis of variance. And variance isn't sum of squares. Variance is sum of squares over degrees of freedom. Too true. Here's degrees of freedom. For the total, it's just the number of scores that you have minus 1. Degrees of freedom is always n minus 1. So it's the number of scores you're considering minus 1. For total, we're considering all 15. And I know it says little n on the screen, but that's just the general formula for degrees of freedom. For total degrees of freedom, which we don't always compute, but we could, it's the number of scores you have minus 1. Between treatments degrees of freedom is the number of means you have that you're considering. In this case, it's 3 minus 1. So we're considering 3 different means and how different they are from each other. 3 different conditions. So 3 minus 1 is 2 degrees of freedom in this case. For degrees of freedom within treatments, it's calculated as big N minus K. That's the number of scores that you have minus the number of groups that you have. But if we go back just a couple slides to here, you can see that the degrees of freedom for the Mozart condition would have been little n minus 1, so 5 minus 1 is 4. For the relaxation condition, it's little n minus 1, which is again 5 minus 1, which is 4. Silence is the same thing, 4 degrees of freedom. And then you just add up all the degrees of freedom within each one of these treatments. So it'd be 4 plus 4 plus 4 is 12. You get the same answer when you follow this formula. Big N is the number of scores you have. K is the number of conditions. It's like subtracting 1 for every condition that you have, just like we did here. So 4 plus 4 plus 4 is 12 degrees of freedom. 15 minus 3 gives you the same answer. It's 12 degrees of freedom within treatments. Why do we do 2 degrees of freedom between and within? That's going to be important when you look up your critical value for F, which we'll do in a separate lecture. Right now I just want to focus on what are we measuring with these different things. Before, we had calculated between treatments sum of squares, which measures variability due to a treatment effect, maybe, individual differences, and chance. Within treatment sums of squares, no treatment effect because they were all treated the same, so it measures variability due to individual differences and chance. From these sums of squares, we divide by the relevant degrees of freedom to get variance. Variance are squares over degrees of freedom. Except in analysis of variance, ironically, we don't call it variance, we call it mean squared. It is the same thing. And when you think about it, that's kind of what variance is. If you have the sum of the squared deviations, you're dividing by not quite the number of scores that you have to get sort of an average or mean squared deviation. That really is kind of what variance is. So mean squared is variance. It's sum of squares over degrees of freedom. We already computed sum of squares between treatments. To turn that into variance, you divide by the appropriate degrees of freedom. Oops. So we've already got between treatments sum of squares. Now we divide by between treatments degrees of freedom to get between treatments mean squared. Similarly, we computed sum of squares within treatments like so, and we divide by the degrees of freedom within treatments that we calculate as big N minus K to get within treatments mean squared. Sum of squares between treatments over 2 degrees of freedom between treatments. Sum of squares within treatments over 12 degrees of freedom within treatments. And that gives us our variances both between and within. I know it's a lot of numbers, and it's a lot to keep track of, so it's handy to draw something like a source table that tells you the different sources of variability. Between treatments, that's due to treatment, chance, and people are different. And within treatments, this also due to chance and people are different, individual differences. And total variability as well. So for each one of these, we have sum of squares and degrees of freedom. We don't really calculate a total variance, a total mean square. It's just not used in ANOVA, so we usually leave this space blank in a source table. But the statistic we're trying to compute is a ratio of between treatments mean square to within treatments mean square. And that statistic is called F. F is the ratio of variability among your means to variability within your treatment groups. Now let's think about what it means. We've split total variability into variability between treatments, which is due to individual differences, chance, and maybe a treatment effect. The other part of total variability is within treatments variability, which is due to not a treatment effect, but individual differences and chance. In taking the ratio of mean square between treatments to mean square within treatments, we're essentially dividing people are different, individual differences, chance, and treatment effect by individual differences and chance. If the null hypothesis is true, then there's no treatment effect, and you're essentially dividing variability due to chance and individual differences by variability due to chance and individual differences. So if there really is no treatment effect, as your null hypothesis will state, then MS between treatments should be very, very close to MS within treatments, and F should converge on a value of 1. When we looked at the T distribution, when the null is true, that most frequently occurring score for T was 0. When the null hypothesis is true in analysis of variance, the numerator is equal to the denominator, and that most frequently occurring score for F shouldn't be 0. It should converge on a value of 1 when the null is true. Because remember, when the null hypothesis is true, the T distribution is centered on 0. But in the F distribution, you're not dividing 0 by a positive denominator. You're dividing this between treatments variance, mean squared, which essentially is a measurement of treatment effect, individual differences, and chance, variability due to those three things. If the null is true, there's no treatment effect, so it's individual differences and chance. We already said that within treatments is individual differences and chance, so you're dividing something by itself, which means what's circled in the graph should have a value of 1. So that's the most frequently occurring F. Both of these are going to be positive. You're never going to get 0, so it actually stops. The F distribution stops at 0. And so F is often reported in a source table just like this. You have sums of squares for between and within and total. You have degrees of freedom for between and within and total. We only compute mean square for between and within. We divide mean square between by mean squared within to get F. And in a different video, I'll show you how to look up a critical value for F and make a decision about that null hypothesis that there's no treatment effect.